Welcome to lecture 3.1. In this lecture, I'll be introducing the concept of aromaticity and how it is even more stabilizing than a standard conjugated system, before we then use aromatic systems as the basis of a topic of chemical reactions. First, it's important to understand that an aromatic system is a type of conjugated system with exceptional stability, right? So we know that conjugated systems are stabilized by their conjugation, and aromaticity is an extra special case, whereas we have great stability. For example, our DNA bases are actually aromatic rings, and we want them to be very stable to avoid random mutation. The typical benzene is what is shown in intro organic chemistry as the aromatic ring. Sometimes it's talked about as the aromatic functional group. But really, aromaticity is a much deeper concept, and there are many more types of aromatic rings, including things such as cyclobutadiene, which is something we refer to as anti-aromatic. So if aromatic rings are extremely stable, anti-aromatic rings are, interestingly, horrifically unstable. And we're going to spend some time figuring out how we can tell, how we can understand this, and how I can look at a ring and determine if it's aromatic, anti-aromatic, or neither. The first requirement for a ring to be considered aromatic is that it is fully conjugated and cyclic. So aromatic systems only exist when they're in rings, but you don't necessarily just have a conjugated system in a ring. The entire ring must participate in that conjugation. These three examples at the top are examples of fully conjugated cyclic rings. Benzene has 3 double bonds, 3 pi bonds, spaced out like such. We see that uninterrupted sequence of p orbitals, right? Fully conjugated. Every single carbon of that ring is involved in the conjugation. Here, we see a 5-carbon ring with a carbocation. Now, using our typical valence bond theory understanding with resonance, we would say, oh, this positive is more stable than you might expect because it's resonance stabilized. That can actually be more complicated, as we'll soon discover, when it comes to rings. But here, in terms of our first requirement, it is absolutely a fully conjugated ring. The double bonds provide their p orbitals, and the carbocation, while it doesn't provide any pi system electrons, it does have an empty orbital, which is used, and we can once again see that it's fully conjugated. This one, a molecule called furan, is similar. Here we see the same 2 double bonds, and one of the oxygen lone pairs could then enter the ring in resonance, making this have some sp2 character and giving us a full ring. Of course, as drawn, remember that this is sp3, but we have to understand that since it is able to participate in that conjugated system, it really has a lot of sp2 character. Awesome. So these 3 rings fit this first requirement. I hesitate to immediately call them aromatic, but I could say absolutely they are fully conjugated rings. Below are 3 examples of rings that are cyclic, but are not fully conjugated. In this first molecule, we see a conjugated system, absolutely a diene that we might see used in Diels-Alder, for example, but there is an sp3 carbon as part of the ring that prevents conjugation, right? And while this ring absolutely has a conjugated system, it is not fully conjugated and therefore not aromatic or anti-aromatic. Any ring like this that is not fully conjugated can be called non-aromatic. We simply don't apply any aromaticity theory when talking about these. So let's look at this next one. Once again, we even see a longer conjugated system. Here we see all these p orbitals, but once again, the ring is not fully conjugated. We have that sp3 carbon. It can't be involved in resonance. It doesn't provide a p orbital. And so despite having a conjugated system, that theory applies, right? This is not going to be an aromatic ring because it doesn't fit the first requirement of being fully conjugated. And the same is true for this molecule as well. Drawing in those p orbitals, we once again see that sp3 carbon that we simply cannot deal with. These rings would be non-aromatic, and these, we could say, pass the first rule in terms of determining if they're aromatic or not. Let's quickly revisit the idea of the energy diagram as it applies to aromaticity. Here we see 3 double bonds that are not conjugated. They're they're interspersed by these sp3 carbons that cannot participate in resonance and are not part of a conjugated system. They're isolated, right? They're unstable because of it. But here, when we take those same 3 double bonds and form a 1,3,5 triene, so 1, 2, 3, 4, 5, right? 1, 3, 5 trienes are conjugated. We draw those p orbitals in, we can see that conjugation. Uninterrupted series of p orbitals, so they're stabilized by that. But suddenly, we take those same 3 double bonds and we make them a ring. And now we have this really, really even more stable, right? There's this extra benefit. If this benefit was due to conjugation, this benefit seems to be due to something different. And this is where aromaticity comes in as this extra idea. Aromatic systems are even more stable than your standard conjugated system. But what's interesting is that cyclobutadiene I talked about earlier is very, very unstable. And if we look at the cyclobutadiene, it fits that first rule we talked about. It is a fully conjugated ring. All 4 carbons have p orbitals, and it is fully flat and conjugated. So what's going on here? What is the idea between this very stable aromatic ring and what we'll learn about the very unstable anti-aromatic ring? First, let's revisit a flowchart. I think a flowchart is a great way to understand this topic. And the idea is that you're going to identify some sort of cyclic system, and you're going to ask, is this an aromatic ring? To get the answer, we first ask that question, is it fully conjugated? Yes or no? If not, we simply call it non-aromatic. But if yes, we're actually not entirely sure. It could be aromatic, or it could be this anti-aromatic idea. In the next video, we're going to dig deeper on how you can understand this aromatic and anti-aromatic principle and predict it using something called Huckel's rule. I'll see you there.